This is ELC 131, Circuit Analysis 1, and the topic is loaded voltage sources. A voltage source is said to be loaded down whenever something causes the source current to increase. The loaded output voltage of a voltage source is always less than the unloaded output of that voltage source. And this is due to the internal resistance of the voltage source. Now, when we see this schematic symbol, we're to assume that this is an ideal voltage source, which shows us that there is no internal resistance associated with this voltage source. And what this means is that when I connect a load to this voltage source, regardless of the value of this load, the load voltage will always be equal to Vs. Now, with a real voltage source, we have to include some value of internal resistance with this voltage source. Now, it doesn't matter if this voltage source is a battery, if it's a photovoltaic cell, if it's a generator, if it's a microphone. Every source of voltage has some internal resistance. And what we see in looking at this circuit is if there is no load connected to this voltage source, then there is no current flowing. And of course, there's no voltage drop across this internal resistance. However, when we connect a load to this real voltage source, now we've got some current flowing. And of course, when we have current flowing, there's going to be some voltage dropped across the internal resistance. And when I have some voltage dropped inside the voltage source, the load voltage, the output voltage of the voltage source, will always be less than the source voltage. So we can make these statements that the no load output voltage of a voltage source is always equal to the potential inside the voltage source, Vs. However, when I'm running this voltage source at what we consider to be loaded conditions or full load conditions, the output voltage will always be less than the value of Vs. Now, in order to quantify the performance of voltage sources, one of the measures we use is called the percent of regulation. And mathematically, the percent of regulation is the no load voltage minus the full load voltage divided by the full load voltage. And again, it's always expressed as a percentage. The closer the percent of regulation is to zero, the closer this voltage source is to an ideal voltage source. Now, let's look at an example. So you see the DMM is connected directly to the output of the 9-volt battery, and we obtain a measurement of 9.34 volts. We'll use this value as the no load output voltage of the battery. Now, I'm going to connect a 91 ohm resistor to the output of the battery. And note, the output voltage of the battery has dropped to 8.62 volts, 8.61. It'll continue to decline the longer the 91 ohm resistor is connected to the battery. But we'll use this value as the full load output voltage of the battery. So we looked at the example of connecting or measuring the output voltage with 9-volt battery. And first, we took this 9-volt battery and connected the DMM to it. Now understand that the resistance of the DMM is 10 megohms. And with a 10 megohm resistance connected to the output of the 9-volt battery, the current that's flowing is approaching zero. It'll actually be in the neighborhood of 900 nanoamps. Because the resistance is so large, because the current is so small, the voltage drop across the internal resistance is approximately zero. So when we measured the output voltage with no load, this was approximately equal to the potential inside the battery, or 9.32 volts. Now we connected a 91 ohm resistor to the battery. And I selected 91 ohms because the full current capacity of this 9-volt battery is approximately 100 milliamps. So by selecting this value of resistor, I was able to operate this 9-volt battery in what I consider to be full load conditions. And when we connected this 91 ohm resistor, we ended up having a voltage across the load of approximately 8.55 volts. Now, the question is, how do we determine the value of the internal resistance? Because this is not something we can measure with the ohm meter. In this battery, the internal resistance is really a layer of H2 molecules, hydrogen gas bubbles, that are formed by the chemical action / reaction inside the battery. It's not something we can measure, but we can determine this empirically. And all we really need to make use of are Ohm's law and Kirchhoff's voltage law. We know that in this closed loop, that V source has to equal VR internal plus V load. And we determined that the source voltage was approximately 9.32 volts. And the full load output voltage was 8.55 volts, which gives us approximately 800 millivolts to be dropped across the load resistor. So we know the voltage dropped inside the battery across the internal resistance. But in order to determine resistance, we have to know two quantities. We have to know voltage and current. But since this is a series circuit, we know the current that flows through the load resistor must also flow through the internal resistance. So we can determine the current in the circuit, I equals V load divided by R load. We know the voltage across the load is 8.55 volts. I measured the 91 ohm resistance and found it had a value of 94.5 ohms. So we yield a current of 90.2 milliamps. And of course, now we can determine the value of the internal resistance by taking the voltage across the internal resistance divided by current. 90 point, oops, excuse me, 800 millivolts divided by 90.2 milliamps gives us a value of internal resistance of approximately 8.8 ohms. So again, this is important in understanding real circuit performance, real circuit characteristics, is that when we connect a load to a voltage source, the output voltage of that source will always be smaller than the unloaded output voltage. Again, this is due to the fact that all voltage sources have some internal resistance. And we looked at an example of a 9-volt battery. We measured the output voltage of the battery with no load connected, and then we connected a 91 ohm resistor to place this battery under full load conditions and measured 8.55 volts, and we could determine the internal resistance of the battery. Now, this exercise is really important for you in terms of when you test a battery. You cannot test that battery by simply connecting a meter to the output terminals of the battery. You must place that battery under load in order to determine its full capacity to deliver voltage and current to a load. When a battery gets weak, it's not because the battery has lost some of the chemicals inside of it. When a battery gets weak, it's because of the internal resistance increasing to a point where that battery simply cannot supply enough current to meet the load's demands. So again, you have to force or place these batteries under load in order to measure them with a meter.